Yeah, good morning to all of you. In this session, I would like to demonstrate another example of handling solids. This has something to do with crystallization and separation of crystals from the solution. You have 5000 kg per hour of an aqueous solution of copper sulfate in water containing 40% of copper sulfate at a temperature of 95 degrees centigrade and 1 bar is fed to a crystallizer. Of course, the recirculation rate in the crystallizer is taken to be 500 kg per hour, and the crystallizer is operating at this temperature and pressure where crystallization occurs. You are required to calculate the mass flow of the crystal product and also do a sensitivity analysis to determine the effect of temperature on the mass flow of the crystal product and also on the non-crystallized product. Now, the mixture of crystals and the non-crystallized part are separated by filtration. So some data is available here. So the solubility data of copper sulfate in water is given in this table. Now let us see how to simulate this problem in Aspen. Now the products, the components that we are going to handle are copper sulfate, water, and you need to talk about the copper sulfate crystals. Let me just show you how to write this. So let me find out the various crystals available under copper sulfate. So you can see from this table, so copper sulfate pentahydrate, so this is what we are interested in, add selected compounds, close. So this is represented like this, but remember this is a solid. Okay, so go to the next step, choose the property model as ideal, go to the next step, simulation environment. Now let us try to look at crystallizers. So this is the one, and we need to separate out the crystals from, you can see, liquid solid separation. So let us say we are using this separator to separate out the solid product. So let us try to connect the inputs and outputs. And this is your liquid and this is your solid. Okay. Again, the moment we are trying to handle solids, let us define the stream class. So we wanted to use mixed CI solid because copper sulfate crystals, which are considered to be the solid in this example, we are able to represent that by means of a molecular formula. So we should be able to handle this as conventional inert solid. So this is the feed material. We know the conditions. I think it is coming at 95 degrees centigrade and 1 bar. So let me provide the data. 1 bar containing 40%. This is in mole flow. Total is 5000 kg per hour. And the mass fractions. Copper sulfate is 0.4, 40%. Water is 0.6, 60%. Okay. There are no inert solids coming along with the feed. It's a solution of copper sulfate. So let us go to the next step. Now, talking about the crystallizer. The crystallizer, we were given that it is operating at 20 degrees centigrade and 1 bar. Right? So these are the specifications required. Next. What is the actual crystals? How is it getting formed? So copper sulfate 1, water 5 gives rise to your product COP01. Coefficient is 1. Right? Then we are supposed to specify the solubility, concentration only. So this data I will try to enter. At 0 degrees centigrade, the solubility in grams per liter is 143. At 10, 174. at 20, 207. So the data is provided in the problem statement. I'm trying to enter the value. 30, 250, 40, 285, 60, 400, 80, 550, and 100, 754. So this was the data that is already given to us. So same data I have entered here, right? Same data. Now we need to talk about this recirculation. So we were given that recirculation flow rate, so which is again in terms of mass 500. Okay. So we have provided required input incomplete. So we need to talk about PhD is not there. Now the issue here is at this point of time there are some crystals getting formed, but did we talk about those crystals? What is going to happen? So this is where no problem. Second part, we have completed the data required for the first. Now this is with respect to the centrifuge. So we wanted to use it as a solid separator, and this data is given. Please refer to the problem statement. So fraction of solids to solids outlet, about 2% is getting lost, and 1% is getting lost in the case, 0.1%. Now, so we don't have to talk about these. Sorry, this pressure need to be mentioned. Now let us look at the stream summary. So, you know the given composition of the feed stream, 40% CuSO4. Now, this 2000 is coming down to 331. What is happening to the remaining? This is the amount of crystals formed, and out of this, 2% is getting lost. So that corresponds to about 52. This is the amount of the crystals that we got from 2610. 2% of this is lost through the liquid stream. Similarly, 1% of this is lost. Now, we were able to find out the compositions and this one, but if you are looking at the Ca substream, you can see what is the quantity of the crystals formed. Copper sulfate crystals, this is the total quantity at the exit of the crystallizer. This is the separated crystals, and some crystals are going through the liquid stream from the centrifuge. So 2% of these crystals are going through this liquid stream, and 98% of crystals you are able to recover by this centrifuge. Of course, there is another small issue that we would like to see. We would like to do a sensitivity analysis to determine the effect of temperature on the formation of crystals. Now let us try to add that model also. Model tools, sensitivity, say new. So what is the variable we would like to vary? The temperature of the crystallizer block, which is B1, and the variable is temperature. Right? We were given 0 to 100. Say in in steps of 5. If you want, as per your convenience, you can do this. So this is what we have. We are varying. What is that we would like to see? The yield of crystals. Maybe formed immediately at the exit of the crystallizer, or if you are interested in looking at the final separated crystals, it's up to you. This is a stream variable. Stream is what is that we want to see? Mass flow. Stream is S2. The exit of substream is Ca solid. Constituent is the crystals. Fill variables. Next. Problem. There were some errors. You can see why those errors. So as the temperature is increasing, obviously the solubility will increase. As a result, the amount of crystals formed will try to decrease. We were operating earlier at a 20 degrees centigrade. So this was the yield of crystals which we have observed earlier. Now, if you are the temperature at which the crystallizer is operating, you will be able to get more crystals. But after this, you can see probably there are no crystals getting formed, so the flow rate was 0. Right? Because of these zeros, it was giving some warnings, but that should not be a problem. Now let me look at the results. So as you can see, the amount of crystals formed is dropping with increase in temperature and ultimately reaching 0 by the time you reach 80 degrees. After that, there are no crystals formed. So this is how you should be able to handle solids using crystallization and maybe separation by using a centrifuge. So let me close this